Hi to everyone, I'm Andrea Fioraldi, a master student from Sapienza University of Rome, and today I'll talk about fuzzing binaries for memory safety errors with QASan. Fuzz testing is one of the most popular and effective software testing technique to discover software vulnerabilities today. It is basically an algorithm that generates random or apparently random inputs for a program under test, and then look if the execution of the program crashed. The challenges and the objective are that we want to maximize the number of founded bugs in a given time. And to do that, we can introduce coverage-guided fuzzing, that is a twist of classic fuzzing, that doesn't generate from scratch the inputs, but mutate input into a corpus and generate the input as a mutation of one or more inputs in the corpus. When the generated input increase the code coverage seen so far during the execution of the fuzzer, this input is saved in the corpus. So, coverage-guided fuzzing is one of the possible techniques to increase the number of faults, and there is a strong empirical evidence that this is true. Look at OSFuzz of Google that uncovered thousands of bugs in open source application in 4 years. Another challenge is that many bugs are not failures. For instance, an heap overflow of just one byte typically doesn't crash the application. So the fuzzer can trigger the bug, but cannot observe that the bug was triggered. So we need some tripwires to uncover this type of silent bugs. Here comes the sanitizer, that are compiler-based instrumentation that uncover this type of bugs. Each sanitizer address some class of bugs. Address sanitizer address memory-related issues like heap overflow, stack overflow, double free, use after free, and so on. Memory sanitizer address the uninitialized read problem, and for instance, thread sanitizer address the race condition, and so on. Typically, some of the sanitizer use a shadow memory approach to be fast. The overhead is very low, like 2 or 3 times. And they are shipped with the most used compiler suite like GCC or Clang. But what about we want to do that fuzz on binaries without the source code? We can still get coverage using some techniques like binary translation, dynamic binary translation that are employed by emulation of DBI, or using hardware support like PT or Hypercalls site, or even static rewriting that is hard to scale and also is hard to do it soundly. But there are a lot of tools and research that improve it with heuristics. And for the sanitization, at the moment, we can do that for fuzzing, of course, only with static rewriting, because the tools that are used to uncover this memory-related issue like Valgrind and Uncheck are not cannot be used for fuzzing due to the high overhead that they introduce, like 100 times respect the normal execution of a program. And the speed is a very important metric in fuzzing, so we cannot really use this type of tools for fuzzing. We can fuzz with QEMU, for instance, one of the most fast options available to fuzz binaries. Using FL++, that is a widely used fuzzer, recent used fuzzer, we can get a very nice performance that is almost 2 times lower than FLGCC that is the compiler-based instrumentation for fuzzing, because we get features from emulation, like block caching and translation block linking to improve the performance. And we also support a wide range of architectures because QEMU is the state-of-the-art in emulation. In FL++ QEMU, there are also included some analysis for comparison instructions to bypass these roadblocks in fuzzing. And a nice feature of emulation is that it can potentially be faster than source-based fuzzing, because to stop or restart a process, there is not the need to use the kernel that is a bottleneck. But yeah, this is a screenshot of FL++ QEMU. As you can see, the speed is nice. But we cannot, at the moment, sanitize binaries with QEMU. We want these features to sanitize binaries. To sanitize libraries, because this is one of the limitations of compiler-based sanitizer. You compile your own binary, not the libraries like the standard C library. And so the sanitizer runtime has to hook the functions of the most common libraries. We want to be fast, but this is almost true with dynamic binary translation. The shadow of memory, we want that it is outside the guest, because one of the limitations of compile-based sanitizer is that the shadow of memory and the metadata are inside the same address space of the target, so that there is a possibility that the program under test corrupt the metadata of the sanitizer. We want an easy-to-use tool with an immediate setup, just download and fuzz. And one of the limitations of binary sanitization is that stack and global variables cannot be sanitized, because this information is removed from the compiler during the compilation stage. Here we are, we built address sanitizer on top of QEMU to enable sanitization while fuzzing with FL++. The architecture of our tool is composed by two parts. One is FL++, but it can be easily replaced with any fuzzer with a bit of engineering, and QEMU. Inside QEMU, QASan is divided in two parts. One that runs inside the emulated target, and one that runs in the host, is part of the emulator. In the target, the read and write instructions are hooked, and the emulator checks the memory accesses using the shadow memory, just like address sanitizer. Also, the function calls are hooked to maintain a shadow stack that is used to report meaningful stack traces when there is an error, both for the faulting allocation and also for the allocation context of the buffer that are involved in the fault. The library inside libQASan, inside the target, hook the allocation functions and insert the typical artifact of a sanitizer, that are the red zone, that are some padding memory zones before and after a chunk in the heap that is invalid memory, so that we can catch buffer underflow and overflow on heap, and a quarantine. A quarantine is to delete the reuse of freed chunks to better detect use after freeze. All of these components communicate breaking the boundary between the guest and the host using hypercalls. And there are two types of hypercalls. One is the slow, that is the fake syscall. Basically, we introduce a new syscall in which you can specify an action, and this has to walk through different dispatcher, the syscall dispatcher and the QASan dispatcher of action. And the fast, that is the backdoor, that access directly to the QASan dispatcher And it is done inserting a new instructions in the target architecture. In this case, in x86-64, you can see that this instruction doesn't exist, and this can be executed only inside QASan, and this is faster than this is called. We also hook some symbols like address sanitizer in case that the user don't want to instrument all the libraries, because yes, we can do that, but of course you pay in performance, because more code you instrument, much more slower will be the execution. So like address sanitizer, we hook common functions used for processing buffers. In this case, string compare. You can see QASan load and QASan store that there are the macro used to check the validity of buffers. We also hotpatch our runtime some function, because hooking symbols using the dynamic loader is not enough, because the libraries will continue to use the internal functions that are not the hooked version. And we want that some functions are never used. For instance, in the C library, there are functions that use that are unwritten, speculate about the architecture and exploits on undefined behavior to gain performance. But this breaks our approach based on shadow memory. So we want to de-optimize these functions, and we hotpatch this function with trampolines in assembly to always use our de-optimized version. This is done during the initialization. In terms of efficiency, QASan is just like all other sanitizer of memory checkers. In this case, you can see that it's slightly better than ASAN, because we sanitize the library. ASAN have hooks, but ASAN doesn't have hooks for all the library's functions, so can miss something. And we are just like a Valgrind check in terms of performance, almost like. In terms of fuzzing, we have a limited overhead. You can see the overhead compared to FL++ QEMU is between 1 and 2 times. That is nice. And we can uncover much more bugs regards normal QEMU in this subset of the fuzzer test suite. Here you can see an example of what a QASan report is. Is this just like address sanitizer, if you are familiar with it? You can see the stack trace for the faulting location, the stack trace then for the buffer that is involved in the fault, and then some information about the shadow memory, just like address sanitizer. For the future, we want to extend this approach for full systems, mainly for embedded devices and IoT firmwares. We want to implement other sanitizer. For instance, the first will be memory sanitizer. And we want to introduce tech use after return in QASan, because yes, this is a state-based class of bugs, but it doesn't depend on the fact that we must know the shape of variables in stack. Thank you for following this talk. I hope you enjoyed it. QASan is free and open source. You can download it from GitHub, and you can fork it for novel research on reproduction of the results. Bye.